Good morning, students. Very nice to meet all of you once again. The previous two classes we had looked at the elastic plastic constitutive modeling, and we have seen how to derive the constitutive matrix during the plastic flow. The fundamental equation we have seen based on the requirement that the yield function value should remain constant, or the change in the yield function value is 0, that we called as a consistency condition. And the actual step by step derivation of that, I have shown it with an example for the joint element, and some other examples are going to be provided in your weekly tutorials and other handouts. Okay, you can go through them. And the next topic that I am going to discuss is a brief introduction to analysis with pore pressures, that is consolidation analysis, and then the dynamic analysis, how to perform the analysis when we have the seismic loading or impact loading or some other such type of loading. And this lecture will be only a brief introduction how to consider the pore pressures in the soil, and then how to perform the consolidation analysis, and then response under dynamic loading. So some of the flow problems are illustrated here. Say the flow through an earth dam, or flow around a sheet pile wall, or a coffer dam, or moisture content determination in the soil. So the first three are for saturated soils, the seepage flow, and of course consolidation. And in all these, whenever we are doing the seepage, we are interested in knowing the topmost flow line, that is called as the phreatic surface, phreatic line that is exposed to the atmospheric pressure. And in the case of partially saturated soils, we would like to determine the moisture and also the suction pressure. And the governing equations for different problems are like this. For the steady state seepage, for analysis of the flow through the soil medium, is the Laplace equation given like this. This is for a 2-dimensional case, and for 3D also we have an additional coordinate, y coordinate. Here the P is the pore pressure, and x and z are the different Cartesian coordinates. And we by doing this analysis and by satisfying the boundary conditions, we can determine the pore pressures at different places within the soil medium. And there are different methods for solving it, both finite difference and finite element. And we can also incorporate the anisotropy. See, what I have shown is only for isotropic soil medium, but it is easy to modify this equation for anisotropic soil with the different coefficient of permeability in x and y directions. And we can also estimate the seepage quantities as k times IA. Is very simple. Once we determine the pore pressures at different locations, you draw a line, and then we can get the gradient, and then the I, the head difference divided by the distance. K is the permeability, and A is the cross sectional area of flow. Then we can also do the transient type problems, which are time dependent, and typical of this is our Terzaghi's one-dimensional consolidation equation. Dou P by dou T is Cv dou square P by dou Z square, where P is the pore pressure and Cv is our coefficient of consolidation. And in these analysis, we would like to determine the pore pressure and displacement, but then if we use the Terzaghi's decoupled theory, there is only pore pressure as the nodal variable, there is nothing else, there is no displacement. And what we do is we estimate the displacements based on the degree of consolidation at different times. But in finite element analysis, we can consider both the displacements and pore pressures by considering other type of consolidation theory. And whenever we are doing the consolidation analysis, we should also look at the increase in the shear strength of the soil because of the consolidation induced compression that leads to a decrease in the void ratio. And some of the new models, latest models like CAM clay, modified CAM clay or soft soil models, they account for this consolidation properties. And you will see some, you will hear some guest lectures on these topics later on. And the simplest analysis with pore pressures is the undrained analysis. Like, assume that your soil or the boundary conditions are such that the pore pressures cannot escape from the soil, and that is an extreme case that we simulate in our consolidation tests, either by UU test or the CU test. And once you do this, once you estimate the pore pressures by some other means, either by using the Henkel's method or the Skempton's method, we can estimate the effective stresses. Here you see the Skempton's equation for estimating the pore pressures in terms of the two principal stresses. This is for 2D case, B times sigma 3 plus A times sigma 1 minus sigma 3, where sigma 3 is our confining pressure or the minor principal stress, and sigma 1 is the major principal stress. Sigma 1 minus sigma 3 is the increase in the deviator stress, and B is your increase in the confining pressure. And once you estimate the pore pressures, the effective stresses are the total stress minus the pore pressure. And when we are doing the undrained analysis, we set the Poisson's ratio close to 0.49, maybe close to, we can even set it to 0.499 depending on the precision that you use. Okay. And if we are doing the effective stress analysis, we need the effective stress shear strength parameters. See, here you see the strength envelopes for both total stress and effective stress Mohr circles. The solid lines, the solid Mohr circles are the Mohr circles corresponding to total stresses. And this particular data is for over consolidated clays, where you develop negative pore pressure. So, there is an increase in the effective stresses under undrained conditions. So, you see the Mohr circles moving to the right, and this dotted line is your effective stress strength envelope, and the intercept and the slope, they give you the C and phi values, and we can use these C prime, phi prime along with the effective stresses that we determine through our finite element analysis, and then we can perform all the calculations like our estimation of bearing capacity or the shear strength and so on. And the strength envelope for normally consolidated clays is like this. So, actually here we see we develop positive pore pressures under undrained loading, and our effective Mohr circles will shift to the left because their effective stress reduces compared to the total stress, and will have a higher friction angle compared to that of the total stress strength parameters. By using one of these methods, it is easy to modify the previously discussed methods for for doing all these constitutive modeling, whether it is bilinear elastic model or our hyperbolic model. Instead of using sigma 3, we will be using sigma 3 prime, and then instead of sigma 1, we will be using sigma 1 prime by estimating the effective stresses, and we can perform the same analysis whatever we have done earlier in terms of the effective stresses. And the other thing that we normally do is the consolidation analysis. That is what happens if you have a drainage that is happening through the soil, and the pore water pressure continues to dissipate with the time, and then the effective stresses increase. And how do we do that analysis? Is actually the one approach that we have is by Terzaghi, but then Biot in 1941 he proposed a generalized consolidation theory, which we call as the coupled theory, because it couples both the displacements and then the pore pressures together along with the compressibility of the soil. And by using that and by using the variational principles, Gabbusi and Wilson they adapted the Biot's theory for finite element analysis. It's actually the Biot's equation is for pure mathematical analysis, but then when you have any say anisotropic soil or non-homogeneous soil or with complicated boundary conditions, we have to use some numerical method for doing the analysis. And Gabbusi and Wilson, they derived the finite element equations. Here I am not showing you the derivation, but if you are interested you can refer to this paper, and the details of this are given in the next slide. We can actually come out with the equilibrium equations, and then the for the stresses or the forces, and then based on the continuity equation and the flow into the volume is equal to the flow out of the volume, or if there is a compressibility, we can include that in the in our continuity equation, and we can derive this equation where u is the displacement vector, p is the pore pressure, and the t plus delta t refers to the next time step. Because actually in all our problems with time, we have a time also as a variable, and these displacements they will go on changing with the time. And on the right hand side, F is the applied force vector, the Q is the seepage force vector. The Q is calculated based on the pore pressures, and here the K is our stiffness matrix of the continuum. C is the interaction matrix between the pore pressures and then the soil skeleton, and here we have the E. E is the compressibility matrix of the pore fluid, and delta is the stability constant, usually taken as about 0.5, and delta t is the time step length, and H is the permeability coefficient matrix, and this could be either isotropic or anisotropic, it does not matter. We can give any variation that you want, and by solving this we can get our displacements and the pore pressures. So actually it's a very time consuming process, because the stability depends on the delta t, and so we have to do a time stepping process to get the solution for the next time steps. And some references are given here. Gabbusi and Wilson in 1973 they developed that previously shown finite element equations that we can solve for getting the solutions. And for solving this type of problems that involve both the displacements and then the pore pressures, we need some other type of continuum element, that is called as a pore elastic composite type element. And here you see one 8 node quadrilateral with 8 nodes, 4 corner nodes and then the 4 mid side nodes, and the pore pressures are defined only at the corner nodes, whereas the displacements are defined at all the 8 nodes. So, the corner nodes, they have both the displacements and then the pore pressures as the nodal variables, whereas the mid side nodes, they have only the displacements as the degrees of freedom. See, the idea is that there should be a compatibility in the variation of strain and then the pore pressure. The strain means its stress. It is the strain and stress are proportional to each other, and it's a quadratic equation in terms of the displacements, and the first derivative is your strain, and that's also the order for the stress. And your pore pressures, because we have only 2 values, one at each end, there is a linear variation, and then the pore pressures also will have the same linear variation. And this type of elements that ensure the compatibility in the variation between the soil stresses and then the pore pressures are more accurate compared to other elements where they define the pore pressures and displacements at all the nodes. Like for example, if you take a 4 node quadrilateral, let me just see. See, let us say you have a 4 node quadrilateral or a 3 node triangle, and by necessity we have to define the displacements and then the pore pressures at all the nodes, and so that means that there is no compatibility between the pore pressures and then the stresses. So, the results that you get with this type of elements may not be as accurate as those we get with this type of elements. Okay. So, for all these analysis we prefer using this type of composite type elements. And when we are doing this consolidation analysis, we will have a problem. See, we see a negative term here, and let us say you have an incompressible, like E is the compressibility matrix, and if you have an incompressible pore fluid, that is the normal usual assumption, E is going to be 0, and for time step, or if you are interested in knowing the initial response at time t equal to 0, delta t is 0. So, you have 0 diagonal terms corresponding to the pore pressure. So, we know that we cannot have any 0 diagonal terms because we will not be able to invert the matrix or use our Gauss elimination process, and for that we have a separate procedure. What we do is we start numbering all the mid side nodes that do not have a pore pressure first. So, when you number a mesh, you can arbitrarily give any node numbers like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let us say all the mid side nodes that do not have the pore pressures can be numbered first, and then let us say we are doing a one dimensional consolidation analysis. Let us take a simple mesh like this. Let us assume that all our elements are 8 node quadrilaterals with corner nodes having both the displacements and then the pore pressures are as nodal variables, and only the mid side nodes they have the displacements. So, what we do is we can start numbering the mid side nodes first. Okay. And then we can number these corner nodes. Okay. There are totally 18 elements in this mesh, and we have three elements. Okay. And so the element 1 will have these, it's defined between 8 nodes, say 12, 11, 13, 14, 1, 2, 4, 3. These are the 8 nodes of element 1. Similarly, for element 2 and element 3 we can define, and since we have numbered only the nodes with the displacement first, we will have all non-zero diagonal terms. So, up to 10 rows means 10 degrees, 10 nodes means 20 degrees of freedom. So, starting from 21st degree of freedom, we may have some rows with some diagonal elements with 0, and in the process of Gauss elimination, these zeros will turn into some non-zero numbers, and then we can avoid the numerical difficulties. And this is one trick that is normally played out for getting the immediate solution. So, this and the consolidation analysis is actually, it's usually done with this type of 8 node quadrilaterals, and by using the Biot's theory, we get the direct solution of both the displacements and then the pore pressures at any time. And if we work with advanced constitutive models like the soft clay model or the modified camp clay model, we can also incorporate the influence of the increase in the soil strength because of consolidation, and so that is an advancement. So, especially if you are doing analysis of any construction on a soft clay, we should go in for consolidation analysis and then go for models like modified camp clay or soft clay models that can include the influence of the void ratio on the strength of the soil. Okay. So, you will hear some lectures on these topics later on through some guest lectures through my colleagues in the department. Now, let us briefly see the dynamic analysis of the soil structures, and the dynamic equilibrium equations, they involve acceleration and then velocity and also the displacements. Like typical equation is mx double dot plus cx dot plus kx is equal to p, where p is our load vector, and that itself could be a function of time. It is not a steady state load, it is not a constant load, it could vary either in a sinusoidal form or arbitrary form. And in this, m is the mass matrix, and that we can write as n transpose rho dV. This is called as the consistent distribution of the mass, and the C is the damping matrix, and could be written as alpha in terms of the mass and stiffness as alpha m plus beta k. This is called as the proportional damping or Rayleigh damping, and it's usually easy because once you know the stiffness matrix and mass matrix, you can get your C, and based on the values that you choose for alpha and m, you can either have a mass proportional damping or stiffness proportional damping, which one is more predominant, that you can decide. And K is the stiffness matrix, the usual stiffness matrix, that is our B transpose B dV, and in here x double dot is the acceleration, x dot is the velocity, and x is the displacement. And so how do we solve this? And it's a time dependent problem, and we have at each node we have acceleration and velocity and also displacement as the variables. So are we going to consider all these three as nodal variables or only one of them? Actually, if you consider all the three, the problem becomes very complicated, because you'll have very large number of degrees of freedom to solve for. And so what we do is we can approximate by different means. The one method is the frequency domain approach. This is suitable for linear elastic systems, where we get the solution separately for different modes and then superimpose, and that is typical for structural engineering problems. And there we cannot incorporate the effect of any nonlinearity or the plastic deformation and so on. Then there is another method called as the time domain method or the direct integration approach, and this is more generic and suitable for any type of nonlinear problems or viscoplastic, viscoelastic or elastic plastic and so on. And we can also include the response under random seismic loading and so on, whereas the frequency domain approach is good, but it is it's only valid for some simple problems. And we can convert our given equations into more simple form by using the difference equations. Here we see the Taylor series expansion of any function f of x around a small variation delta x. It is f of x plus delta x is f of x plus delta x times f prime x plus delta x square f double prime and so on, and f x minus delta x, like you can either add delta x or subtract delta x, and then these are the Taylor series expansions. And by manipulating this, we can develop the forward difference schemes, backward difference schemes, central difference schemes and so on. And the central difference scheme is a more preferred one, because you can get convergence faster, as we see here. So if you want to get the f prime x by forward or backward difference scheme, we can neglect all the higher order terms from delta x square, and then we can write f prime of x is f of x plus delta x minus f of x by delta x, and the error is of the order delta x, because all the terms above that are eliminated. Whereas if you look at the backward difference scheme is also the same. By looking at this, we can write f prime of x is f of x minus f x minus delta x by x delta x, and by central difference scheme, if you add up these two equations, if you subtract, f prime of x can be written as f of x plus delta x minus f of x minus delta x by 2 delta x, and then this term gets eliminated, and you have the order of delta x to the power 3. The error is of this order, and if delta x itself is small, delta x cube will be even smaller. And we can also determine the double prime f double prime by adding these two equations 2 and 3, and we get slightly different equation. And here the error is of the order delta x to the power 4, because we are neglecting the terms starting from delta x to the power 4. Okay. and this equation for f prime x is actually our x dot. This is related to your first derivative, that is velocity term, and this is our second derivative related to our acceleration term, and we can substitute this in our governing equation mx double dot plus cx dot plus kx is equal to p, and convert the entire equation into only in terms of displacements at different time steps. And when we do that, we can do in two different ways. One is an explicit method, central difference scheme, a conditionally stable algorithm is actually it is these explicit methods, they are only conditionally stable, whereas implicit method is actually we have the unknown terms both on the left hand side and the right hand side, whereas in the explicit method all the unknown terms are on the left hand side. On the right hand side we know all the quantities, they refer to the previous time step, whereas in the implicit method the terms, unknown terms are both there on the left hand side and the right hand side. Okay. The central difference scheme is like this. Our acceleration at time t we can get by looking at the displacements at two different time steps, ut plus delta t and ut minus delta t, and then the time the displacement at this time step ut like this, and the velocity at time t is the difference in the velocities at time t plus delta t and ut minus delta t by 2 delta t, and we can substitute these two expressions in our governing equation, and then we can convert our equation and we get a matrix like this. Sorry. So our the u double dot and u dot, once you place and then our displacement at time t is a known quantity and we take to the right hand side, whereas the displacements at time t plus delta t are unknowns, and so we retain them on the left hand side, and so we have on the right hand side the load at time t minus the k minus 2 by 2 delta square m times ut and so on, and then on the left hand side we have some effective stiffness matrix m by delta t square plus c by 2 delta t times displacement at the next time step. Okay. And so we can repeatedly solve this equation and then get our solution. Okay. But let us say we are interested in first knowing the response at time t equal to 0. So if you substitute t equal to 0, that is the response at delta t, we have this u naught, that is our initial conditions. But then if you look at this, the displacement at the previous time step, u at minus delta t, that is even before we start applying the load, we should know what happened before that. And but there is a method for getting that, but once you get it, then it is a simple recursive equation. We go on getting the solution at time delta t, 2 delta t, 3 delta t and so on by time stepping scheme or by the time marching scheme. And the starting procedure, the displacement at time minus delta t, we can get by setting this to the time to t to 0, and then we can get the displacement at the previous time step as u naught minus delta t u dot 0 plus delta t square by 2 acceleration at initial time step. Okay. And once you have this, we can do the time marching scheme. Okay. And so this is what we can do for converting our differential equation in terms of the displacements. Displacements are different time steps, t plus delta t, t minus delta t, and so on. And this is the explicit method, where we have all the known quantities on the right hand side. So if you look at this, all the right hand side terms, they are either corresponding to current time t or the previous time t minus delta t. And so we can and of course the load at this current time t, and we can easily form the right hand side vector, and then the left hand side is the unknown, the displacement at u t plus delta t. And this is our explicit method or explicit equation for solving, and it is a good procedure, but only thing is it is conditionally stable, that we will see with a numerical example. For some delta t's, you might not get any convergence. And there are other methods called as implicit methods. Let me get my laser pointer. And these implicit schemes are unconditionally stable. Whatever may be the delta t, you get a stable solution. And some methods are by Hubolt, Wilson theta, and then Newmark's method. In this lecture, I am explaining only the Newmark's method. The other methods are very similar, very similar to Newmark's method, and you can refer to any good textbook for getting the details of the other methods. And in the Newmark's method is called as the average acceleration method. The velocity at time step, the next time step t plus delta t, we can write in terms of the velocity at time t plus 1 minus delta acceleration at time t, and then delta times acceleration at time t plus delta t multiplied by delta t. See, here is the velocity plus acceleration times delta t is your velocity. So, you see here, you see the implicit nature of this equation, because you have the velocity at time t plus delta t written in terms of acceleration at t plus delta t, and t plus delta t refers to the next time step, for which we need to know the solution, we need to determine the solution. Okay. And similarly, our displacement at time t plus delta t, we can write like this: the displacement at time t plus the velocity at time t multiplied by delta t plus the average acceleration multiplied by delta t square. And this delta and alpha are called as integration parameters. We have to choose them so that we get stable algorithm. And if you substitute these equations in our governing equation mx double dot plus cx dot plus kx is equal to p of t, we can convert them into some equivalent stiffness matrix k hat. U t plus delta t is the force vector at t plus delta t, and the force vector is a known quantity, and then our displacement at the next time step t plus delta t is the unknown quantity, and the k hat is written as k plus a naught m plus a1 c, where a naught and a1 these are some constants that we will see later, and r hat is the effective load vector at time t plus delta t, that is sum total of the applied loading plus mass times all these quantities and the c times all these quantities, which are all dependent on the values at the previous time, the displacement at time t, velocity at time t, acceleration at time t, and so on. And so the load vector we can easily determine, because r t plus delta t is the applied load, and so we know what is that applied load, and our delta and alpha are chosen like this. Delta should be greater than or equal to 0.5. Usually we take it as 0.5, and alpha should be greater than 0.25 times 0.5 plus delta whole square, and if delta is taken as 0.5, alpha comes out as 0.25, and a naught, a1, a2, a3 and all these parameters they are given here. Basically we get them by substituting these terms in the governing equation and simplifying, we get these terms, and delta t is the time step length that we can fix. And once the displacements at time t plus delta t are determined, then the acceleration at the next time step is a naught times u t plus delta t minus u t minus a2 times u dot t minus a3 u double dot t, and then the velocity at time t plus delta t is obtained like this. Is actually basically we can use these equations to get our to get these quantities, because we know what is acceleration at time t plus delta t, and then we substitute that and then get our velocity at the next time step. So let me show you one example. This particular one is from oops, what happened? What's happening? Okay. Yeah. This particular one is the finite element mesh for Koina Dam, and the Koina Dam is a reinforced concrete dam, and this particular result that I am going to show is from Abacus program, and it was subjected to some earthquake acceleration because of the hydrostatic pressures, and then because of the water penetrating into the ground, and that has caused some earthquake. And basically it's not an earthquake prone zone, but then it is subjected to earthquake, and the geologists think that because of the voids in the ground these earthquakes happen, and the recorded earthquake accelerations are given here. This is the transverse ground motion, and then this is the vertical ground acceleration, the acceleration with the time, and the record is given for 10 seconds, and this was applied at the ground level, like we take all the nodes corresponding to the base and apply the acceleration, both acceleration in the horizontal direction and then the vertical direction, and we can get our displacement. And here is an animation for the displacement. So, basically what the program has done is it has performed the analysis, saved the displacements at different time steps, and then plotted the displacement shape at different time steps. Continuously it has started plotting, and it comes out as in an animation form like this. And we are interested in knowing the stresses, and because of this the change in the cross section here, this is the most critical area where the concrete was subjected to lot of tensile stresses, that we can see through this animation. We can see the red dots that indicate the tensile stress. All these red dots they indicate the locations where the tensile stresses are more than the capacity of the concrete, and we can assume that all these zones have failed. In fact, when you compare the damage that actually happened in the dam to the finite element predictions, they both matched very nicely, and at different times there is a different damage, and these are all the red zones. These are the damaged portions. Okay. And actually this particular example that I showed was solved by this Newmark's method, by the implicit method. And let me demonstrate one simple numerical example. This I am showing only for understanding purpose, and a similar procedure is also followed in finite element analysis, but then you will be dealing with much larger problems. Let us consider a system, a 2 degree of freedom system without any damping, and this is our mass matrix, and there are only 2 degrees of freedom. The acceleration at degree of freedom 1, acceleration at degree of freedom 2, and then the stiffness matrix, the displacements u1 and u2 is subjected to loading, the instantaneous loading, and then we want to know what happens with the time, what are the displacements and what are the other quantities. And there are 2 degrees of freedom, so we will have 2 fundamental periods. The T1 is 4.45 and T2 is 2.8. This is corresponding to mode 1, and this is corresponding to mode 2, and usually the fundamental the first vibration mode will have a higher higher time period compared to the higher orders of vibrations. So, T2 is 2.8, T1 is 4.45, and let us solve this system by using the explicit method, the central difference method, with the delta T of T2 by 10 and delta T of 10 times T2, that is 0.28 and 28 seconds, and delta T how you choose, not only based on the stability, but if you choose a very large time step, you will be missing out the initial response. So, even 0.28 may not be sufficient if you are interested in knowing what happens at short time intervals, because it is actually this loading is applied instantaneously, and we are interested in knowing shortly after the load is applied, like milliseconds. In that case, the delta T may be even smaller, and as the time progresses you can increase the delta T so that you can accelerate much faster. Let us take to start with a delta T of 0.28, and we need the response at the previous time step, T of minus delta T, and the equation for the starting the analysis is given here, and the U1 and U2 at time step minus 0.28 are 0 and 0.392, and our initial velocity and acceleration are 0 and 0. Sorry, I think where is the initial displacement and velocities are given as 0. And we can get the initial acceleration by putting in the initial displacements in our governing equation, and we get the U1 and U2 acceleration as 0 and 10, and we use that value here, and we get the displacement at degree of freedom 1 and 2 at the time step minus delta t, like this, and then this is our k hat, and the effective stiffness matrix is m by delta t square and c by 2 delta t, and this is our it's a constant value in the explicit method, and then the effective load vector, the right hand side, is given like this, and as the displacements are changing, the right hand side will go on changing, and we can solve this recursive equation, and we get the solutions at different time steps, delta t, 2 delta t, 3 delta t, 4, 5, 6 and so on. I have solved up to 12 delta t, and these are actually manual calculations. You can just simply take a calculator or write an Excel program and solve them. It's very simple, and we see that as the time step is increasing, the displacement is fluctuating, and at 12 times the delta t, 12 times 0.28, the displacements are 1 and 2.6, and we can continue like and because there is no damping, the motion will continue forever, because we didn't consider or we didn't include the damping. Okay, and let's now see what happens with a delta t of 10 times the t2, 28 seconds. Why do we want to use 28 seconds? That is, if you want to know what happens at a large time interval, if you use a larger delta t, you need to spend a lesser computational effort, and we can go through the time much faster. But then if you use a delta t of 28 seconds, this is what we get at the starting time step delta t. Our displacement is some 3830, and at 2 times the delta t, the displacements are even larger. So we can say that it has started diverging, and so it's an unstable solution. Like although it's a numerical value, it's giving some displacement, but it's actually it's an unreasonable value, because with delta t of 0.28, even after 12 times or 12 iterations, we get a reasonable displacement, and we see that with a larger time step, there is no convergence, the solution is diverging. So that's the disadvantage with the central difference scheme. Although it's a very simple scheme, but the stability depends on the delta t. And now let's look at the Newmark's method, and let's solve with delta t of t2 by 10, that is 0.28, and then 10 times the t2, that is 28 seconds. Okay, and these are all the constants a0, a1 and so on, and the effective stiffness matrix k hat is this, and then the right hand side load vector is like this, and the displacement at any time t plus delta t is k hat multiplied by u t plus delta t is r hat at t plus delta t, and then we can continue the solution. And so for 10 iterations, like this is the solution with 0.28, and it's once again fluctuating. The solution is not the same. Okay, and you see that this solution is different from what we get from the central difference scheme, and actually this the Newmark's solution is better, more accurate compared to the central difference scheme. And if you compare this and that, there is some difference, and with a delta t of 28, this is the response that we get. And in fact, once again we are getting up and down because there is no damping. Okay, and after 10 times the delta t, that is the 280 seconds, our response is still within the finite values, like 0.648 and 1.04 is going up and down. Okay, whereas with central difference scheme, the whole thing has blown up. Okay. So this shows the advantage of the implicit methods. This is particularly the Newmark's method, and similar solutions you can get even with the Wilson theta method or the Hubolt method, and both of them are very similar to this Newmark's method. So before I close, let me just show you an Excel spreadsheet program. I want to keep the annotation. So you have a Excel spreadsheet program for Newmark's method, and this particular one is for a single degree of freedom. Okay, it's this particular one is for impulse loading, and you can actually, these are all the delta is 0.5 and alpha is 0.25 as we discussed, and then the mass is given, stiffness is given, and you can calculate the critical damping of the system. Okay, and then the loading is given here. The peak load is 500 seconds, and then the duration of the impulse is given here, 0.05, and then we can get the response by Newmark's method. It's a very simple one, like it's even simpler than the 2 degree of freedom example that we considered earlier. And let's calculate the response without any damping. Let's say there is no damping. Okay, and you see here the response is given here, like it is actually it's a beautiful sinusoidal response. There is no reduction in the displacement because there is no damping. Okay, and now let's consider some damping. Let's say some 0.01, very small damping, and then we see gradually the displacements are reducing with time. And if we use larger value, like let's say 0.1, and this damping factor here, we are using damping factor. The damping is damping factor multiplied by the critical damping factor. Okay. And here you see a beautiful reduction in the displacements for higher damping ratio. And if you use a very large damping ratio of 1, if the damping is more than the critical damping, you don't get any oscillations. You directly get your the constant displacement. This is what you get here. There's too much of damping, and within a small time the displacement has become 0. And you can actually, it's a very simple spreadsheet program that lets you examine the influence of different time steps. Like here the delta t is suggested, I think based on based on the H6 is what based on the impulse loading, and the delta T is what you can suggest you can include. Let me just use a very small very large value delta T. Oops, sorry, I think delta T is too large, because actually it is larger than the impact duration, impulse duration, so you will not get anything. Okay, because your impulse duration is 0.05, and if you use a delta T of greater than the impulse time, you will not get anything. Okay, with this and we can try even with the 0.05. Let's try with the 0.01. Okay, and you will get some response. Okay, and say if you use a 0.05 within one time step, you are at the end of your impulse. So you will not see any response. It is not the numerical instability, but it's the you are beyond your impact loading. Okay, so your delta T should be proportional to your impact duration. Okay, so let's say we use a larger value. Okay, larger value of 1 second, and even with 0.1 you'll get a reasonable response. You'll get you'll get a different shaped response, because now your it's not really impulse loading, it is just stayed on the system for a longer time. So you'll get this type of confusing response. It's like I'm applying for a smaller time step. Okay, and you can see is actually depending on the way you apply the loading, and depending on the duration of the loading, you get a different response. And you can look at the influence of your damping ratio, and then the impulse duration, and then the stiffness coefficient and other things. Like here the stiffness is given as 2000, and let me just give this as a real impulse 0.005. Okay, and here oops, what happened? Oops, what happened? Okay, we get a displacement of about 0.0, maybe 0.065, and let's increase the stiffness. Let's say we are increasing to 5000. Okay, and you will see the displacement has reduced 0.04. Okay, and then you get a different response, because now our critical time period has changed, and then the way the system responds is different. Okay, so you can examine all these factors using this simple Excel spreadsheet program, and this particular one is based on the Newmark's direct integration methods. So that's a brief introduction to analysis of the systems with pore pressures, and then the dynamic analysis. I try to give you a simple examples, numerical examples with hand calculations, so that you understand the procedures, and a similar procedure is followed even in the finite element analysis. So if you have any questions, please send an email to this address profkrg@gmail.com, and this will be my last lecture in the course. but this will be followed by some guest lectures by my colleagues who will be talking to you on other constitutive models, our constitutive models like CAM-clay models, modified CAM-clay, and then other critical state models, then soft clay modeling, and then some practical analysis using Plaxis program. Okay. So I have about 5 guest lectures that also they will be uploaded on the course website. You can go through them, and there will be assignments and other things that you need to solve for your grading purposes. So thank you very much, and look forward to interacting with you further on any of these topics. Okay, thank you very much. Bye.